Okay, beautiful. All right, we start the last material today that's going to be on the next exam. It's not complicated, it's just different. We're going to throw conditions for the first time. We're going to throw conditions. We're going to say, what is the probability of something happening given that we know information? Given that we know information can affect, it might not, but it can affect the probability. So I'm going to start with a really simple question. I want to roll the dice. Roll the fair dice. Again, it's implied that they're fair. Now, let's find the probability the sum is at least 8. Let's start with that. Now, how would you do it? What's the easiest way, the laziest way humanly possible to answer this question? You're going to do some calculations, you're going to list some things. I have a dice roll chart on the board. I'm lazy. I'm going to go up to the dice roll chart and say, all right, at least 8 would be that. You with me on that? That's the easiest way to do this. So if I said, what's the probability of at least 8, how many outcomes did I just circle?
57. 16.
1 plus 2 plus 3 plus 4 plus 5, 50. I've circled 15 outcomes. Everybody agree with that? So what would be the probability? You'd say 15 over 36. That seems like a really simple thing. Yes, I can go back to my table and say, what's the probability of rolling a total of 2, 3, 4, 5? I can do that, I can count them up, I can add them up, or I can just be really lazy. Okay, so I'm rolling the dice and you're getting ready to make your bet, and I say, okay, what's the probability I'm gonna roll at least an 8? And you're deciding whether to wager on that or not. And while I was talking, you know, Matthew says, hey, Mr. Brown, look at that. And one of the dice slipped out of my hand. One of the dice slipped out of my hand, and you saw one of the dice is 6. Now, I haven't finished my roll. And you know, you're on your computer getting ready to make your computer wager, and in those 2 seconds that you have before I finish my roll, you saw one of my dice was a 6. A moment ago, the probability was 15 over 36, but you saw one of my dice was a 6. Does that change the probability now?
Yes.
Why? It's actually a really simple reason, and this is the most important part of the process. What is my sample space before I start?
15.
No, my sample space is
Oh, yeah, the whole thing.
36 rolls. When you saw that one of the dice squirted out as a 6, what changed? Don't think the probability, my sample space changed. What did my sample space change to? My sample space changed Does everybody understand? My sample space just changed to those rolls because you saw one of the dice was a 6. Still the same question. Now, 15 out of 36, if you're a gambler, that's not terrible. That's over 40%. Okay? That's not terrible if you're a gambler. But if you saw one of the dice was a 6, now what's your probability that my sum is at least an 8? What is it? 9 out of 11. If you're a gambler, would you take those odds? Oh, I think you would. Okay, knowing that one of the dice landed a 6 affected the probability. So this is what we're going to call conditional probability. And there's notation. Conditional probability, okay? Because I'm giving you a condition and it did affect the probability. So let's go back here. I want to know what's the probability my dice is at least, my sum is at least an 8. So let's call that our first event. Let's call A, sum is at least 8. Let's call B the event, one of the dice is 6. Now, I don't know which die, doesn't matter. I mean, could they both end up being 6s? Sure. Okay. What am I looking at now? I'm looking at an intersection. That the sum is at least an 8, and one of the dice is a 6. Does everybody agree with that? And that would be, you said 9 rolls? That would be these 9 rolls that are between the orange and the blue. Okay? You said the answer to this question here was 9 over 11, and that is the correct answer. So the question is, how do we get from there to there? Okay, so let me give you a little bit of notation. The notation, this is general. The probability of A, vertical bar, B, this is the probability of A given B. In other words, what is the probability of event A occurring given that we know event B occurred? Okay. Vertical bar, this is not a quotient. So vertical bar we know is used in a lot of different contexts, isn't it? I mean, we use it in set notation. It's one of these confusing symbols. In this context, it means conditional probability. In any probability context, whenever you see a vertical bar, this is the only use you'll ever see it for. So the probability of A given B has occurred. So now I am asking you, what is the probability that my sum is at least an 8 given that I know one of my dice is a 6? Because the first probability you said was just 15 out of 36. But the second probability you said was 9 out of 11. So how do we get there? Well, what does A intersect B in this case? That's sum is 8 and one of the dice, and one of the dice is 6. By the way, that means I know one of the dice is 6. It doesn't say that you can only have one 6. I just know there is a 6 in the middle. I mean, could it end up being double 6s? Sure, because I don't know what the other die is. So what is the probability? Let's do each of these probabilities. What is the probability of A again? We said that's 15 over 36. What is the probability of B? What is the probability that one of my dice is a 6? How many rolls have a 6 in them? 11. So that would be 11 over 36. And the third one, what is the probability of my intersection there? What is the probability that the sum is an 8 and at the same time one of the dice is a 6? Well, that was, what, 9 rolls? You with me? So that one would be 9 out of 36. These are what we know. So just the probability of event A occurring, B occurring, the intersection occurring. Now my question was, what's the probability of A occurring given that B occurred? And you just simply counted and got this number. You didn't do any math, right? We just counted. Where does that number come from in here?
Probability of A and B over probability of B.
It looks like if I took the probability of A and B together divided by the probability of B, that would give me 9 over 36 over 11 over 36, and that's my answer. It turns out that is the formula. And here's why. Let's go back to the beginning of the problem. When I said I'm just going to roll the dice, what's the probability my sum's at least an 8? You counted and you got 15 out of 36. When you saw one of the dice squirted out of my hand inadvertently, and it landed a 6, I no longer have 36 dice rolls in my sample space. I only have 11 dice rolls, because there's only 11 dice rolls that have a 6 in them. So the moment you knew the condition, you changed the sample space. So my denominator is no longer just simply 36. My denominator is what did my sample space reduce to? In this case, it was now 11, wasn't it? So how do I do that mathematically? Turns out to be this. So the formula for conditional probability, and it is always the same formula. It's always this. This is the formula. Because this means I changed the sample space. Knowing B has occurred changes your sample space. So, same original problem. I'm rolling the dice and I want to get a sum of at least 8, right? Whatever game I'm playing, I need at least an 8. And again, I'm being kind of careless and I'm distracted. And this time, you saw that one of the dice rolled out and is a 1. If you're a gambler, are you going to bet on this one? Probably not. Why?
2 out of 11.
What's the probability my sum is at least an 8, this time seeing that one of the dice landed a 1?
0.
0. Why is it 0?
Because 1 plus the highest value you can have, which is 6, doesn't
Oh,
make it.
because the rolls that have 1s in them
Don't-
are these rolls, and not one of them adds up to an 8. Oh, that's totally different, isn't it? So in this case, the intersection would be empty. There are no rolls that add up to at least 8 and have a 1 in them. Do we agree on that? Oh, okay, so that would completely change things. Okay, so conditional probability, I could end up getting a probability of 0 as a result. Yikes. Now, I can change the question. Let's change the question. I want the sum is going to be at least 5. And now you saw one of the dice squirted out and landed a 6. Now what's your probability?
100%.
It's going to be 1, isn't it? Because every roll would be, okay. So in this case here, the dice rolls, it's actually a fairly simple process. Does everybody agree with that? I can just simply count it. What if I have a situation where I don't have this picture and I can just simply count the outcomes? We started with something really easy. This was very simple for us to count and it made sense. And now we're working backwards on the mathematics. So again, whatever the sample space for the original problem is, what this does is reduces the sample space. So here's an easier way to think about this. Okay, erase this. Okay, if S is my sample space, and A is the event, then we know the probability of A is what? The number of outcomes in A over the number of outcomes in the sample space. We know that. That's the definition. So now if I look at it from this point of view, you're saying, oh, this is the same as saying the number of outcomes in A intersect B divided by the number of outcomes in B. Because both of these had this in their denominator, didn't they? Remember, the probability of something happening means I have to divide it by this number. So my numerator was actually the number in the intersection divided by the number in the sample space. Here's the number in B divided by the number in the sample space. Well, algebraically those would cancel. So really it comes down to this. The condition determines everything. Okay? My condition that B had to occur means the only part of the sample space I'm considering are those outcomes in B. So I'm no longer dividing by the number of outcomes in the sample space. I'm really dividing by the number of outcomes in B. Hopefully that makes sense. So now going back to this problem. I could get the 9 over 11 without doing the quotient because my sample space reduced to 11 outcomes when I did this. And I just counted 9 of them. Isn't that nice? It's beautiful, but it's almost never this simple. And that's why we start with this one. So, all right, any question on this? Unfortunately, I have to erase this. My beautiful work here is now over stream. All right, so in a recent poll of San Diegans, okay, we're gonna agree it's accurate. We found that 40% go to the beach. Let's say at least once a week, okay? Let's say that we found that 60% exercise regularly. And let's say we found that 30% do both. Okay? Now, I'm telling you the percentages of San Diegans doing things. Do I need to know the exact number of people that is? Do I need to know how many people live in San Diego and now figure out exactly how many go to the beach? Do I need that information, or is that good enough, do you think? Because now, because I gave you percentages, it doesn't matter if it's a small population or a big population. It's 40% of the population. That's it. Now, I need to convert these to probabilities, okay? Because I'm going to ask you several questions. Now, let's assume that this information is accurate. Let's assume this information is factual. Because otherwise you'd say, well, I don't trust any of my answers, and that's not the case. Okay. Let's say, let's call B the event, you're a beachgoer. And let's call, how about E the event that you exercise. Exercise, spell exercise regularly. Okay, then obviously B intersect E is you do both. Okay, do we have probabilities now? What is the probability of someone being a beachgoer? What is the probability that someone exercises regularly? What is the probability that you do both? And the beauty here is I do not need numbers, right? I do not need to know how many are in each of these sets. What is the probability of San Diego? Here's an easy way of thinking about it. I'm going to select a San Diegan at random. What is the probability they are a beachgoer? We'll leave it as decimals. It's just easier. Yes, that's absolutely correct. I could write it as a fraction, but in this context, it might be easier to write it as a decimal because we will assume that these are accurate numbers. So how about 0.4? How about this? 0.6 and this? 0.3. All right, so what kind of questions can we ask? Well, let's ask some easy ones. First question, and I want you to do all of them. What is the probability someone does either A or B? What is the probability someone does neither A nor B? What is the probability a beachgoer also exercises? What is the probability an exerciser? An exerciser, how's that? Exerciser also goes to the beach. Now, I could do things like, okay, what's the probability someone goes to the beach and does not exercise? We'll even do more. Okay, what's the probability that somebody exercises and does not go to the beach? Yikes. Let's start with this. Now, maybe the simplest way to attack this problem from a conceptual standpoint is to draw the Venn diagram, because I only have 2 circles. It's pretty easy when it's only 2 circles. A little more complicated when there's 3. So we have the beachgoers, we have the exercisers. Now I need to put the numbers in. Where do you start? We talked about this before. You always start in the same place. Whether there's 2 circles or 10 circles, you always start in the same place. Where? Out here, 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 here. There's actually multiple regions. Technically, there's 4 regions here. You can only start in one place. It has to be the intersection. You always start in the intersection and you work out. Because if I put these numbers independently in the situations, it's going to add up to more than 1, isn't it? There is no 0.4 anywhere in my picture, in other words. There's no 0.6 anywhere in the picture. So I start with the 0.3. Now, what's here? 0.1. How come 0.1? Because the whole circle has got to add up to 0.4. Ah, that changes things, isn't it? So what's here? And what's out here? I could have been more creative, I suppose. It's also 0.3. Okay, a lot of 0.3s. So the first question, what is the probability someone does either A or B? So the first question is, what is, okay, I really hate this stuff. Someone's just being evil, they're putting caps that are different colors on the pen. All right. First question is, I'm actually asking what?
Probability A union B? Or-
Good.
Or B union.
No, the order doesn't matter, yeah. So I'm sorry, not A, B.
Yeah, that's my.
Thank you, that's what you meant to say, B, union, E. Does everyone see that? I'm asking for the union because I said, you're doing this or you're doing this. So how do we answer this question? There's actually a formula. Isn't this probability of B plus probability of E?
Subtract the.
Minus the probability of the intersection. Because if I simply did the probability of B plus the probability of E, I'd be at 1. Now, all San Diegans, but wait a minute, there's a whole bunch of San Diegans out here. These are the unhappy San Diegans, by the way. All right? They don't do anything, they just sit around and watch TV all day. So this is 0.4 plus 0.6 minus 0.3, and that's clearly 0.7. So the probability somebody does either one is 0.7. Now, this is not an exclusive or, right? You do either one or both. Both is still fair game. So what's the second question? I'm asking you, someone does neither. So how can I write that in a notation standpoint?
You have not B.
You can say probability somebody does not do B and at the same time does not do E. Well, wouldn't that simply be the probability of B union E complement? So in other words, I asked you for this. So mathematically, what would we do? 1 minus the probability of B union E. I want to write down the formal notation so we know where everything is coming from. Okay? So this answer is what? 1 minus 0.7 or 0.3. Well, that's apparent in our picture, but we want to actually do the mathematics. Now, the next two questions are kind of tricky. What's the probability that somebody goes to the beach? Sorry, what's the probability that a beach goer also exercises? So I'm asking you, not what's the probability of somebody going to the beach. No, I'm asking you, what's the probability that somebody exercises given that you know they go to the beach? My sample space is only beachgoers. Does everybody see that? That's the trickiest part of this. My sample space is now only the beachgoers. I'm asking something about a beachgoer. What's the probability that a beachgoer exercises? So the third question is, what is the probability of somebody exercising given that you know that they go to the beach? So now look at this circle. Just give me a common sense answer. Look at this circle. I know they go to the beach. What's the probability they exercise? That's most of them, isn't it? I mean, most of the beachgoers are exercisers. How do I write this mathematically? It's the probability of the intersection over the probability that they're a beachgoer. And what's the probability of the intersection? 0.3, and beachgoer? 0.4. So if you want to say 3/4 or 0.75. Oh, is that an oh duh looking at the picture that it's 3/4? Would you have gotten that looking at this information? No, you don't see it right there. But now, because I drew the picture, that's a fairly easy thing. You don't have to draw a picture to answer the question. In this case, the Venn diagram really helps. So what's question number 4? It's a similar question, but it's not the same question. I'm now saying, what is the probability that an exerciser also goes to the beach? So now I'm looking at the circle that only consists of exercisers, and I'm asking, what's the probability a person goes to the beach knowing they come from the exercise group? That's the thing, you have to take it apart. It's very easy to read this and get the B and the E backwards, isn't it? It's very easy. But what do I know? Where is my sample space? Here the sample space is only beachgoers. Here the sample space is only exercisers. So the thing I know is that these are exercisers. Okay? Now I'm asking which ones of them go to the beach. So this question is, what's the probability somebody goes to the beach given they're an exerciser? It's not the same question, but it does have the same numerator. Okay, but now my denominator is this. So what is this answer? 0.3 over 0.6, and that's half. So in English, you could say half of all exercisers go to the beach, but 3/4 of all beachgoers also exercise. Okay? So far, so good? Is that complicated in this context? No.
Actually, I did have a question about the neither A nor B part. So that's not.
Yeah,
not
nor
B.
means both are nots at the same time. So if you say A, neither A nor B, you're saying not A and at the same time not B. You're not either one of them. You're not this one or you're not this one. That's why neither nor, a lot of people mix up those words English-wise. If you're neither going to the store today nor the beach, that doesn't mean you can do one of them. That means you're not doing either one of them.
At the same time, okay. I see.
So that's why it's a not and in that case.
Okay.
It's a this and, it's not this and not this, so I'm not doing either one of them, means I'm not doing the union.
The nor is like an and in this case.
Yes.
Okay, I see.
And neither nor. This is one of those things that's a little bit tricky English-wise. When you guys were translating things earlier, I said avoid translating into neithers and nors because we often get the ands backwards. But if the statement actually is neither and nor, I could have said it, what is the probability somebody does not go to the beach and at the same time they do not exercise? It's too many words. They don't go to the beach, and neither nor. It's efficient words, but we have to understand it. Now, I just gave you two conditional probabilities, and that was very, very different. Let me ask you a simple question. I know what the probability is that somebody goes to the beach. Does that probability change if I know they exercise or don't exercise? Okay, so I'm going to ask you a fifth question. Question number 5. What is the probability someone is a beachgoer oops. Hold on. So what is the probability someone is a beachgoer and don't exercise? Okay. Is this a conditional probability or is this an intersection?
Intersection.
This is an intersection. How do you know? Because I'm putting two things at the same time. I'm saying, what's the probability of this and this? Let me erase this. So how do I do that one? By the way, this question, this is one of my all-time favorite questions to ask you on quizzes and tests, because the mathematics of the question is not hard. I mean, I'm taking quotients of number. I'm just basically one quotient after another or one statement after another, but it's knowing where to pick apart. So what am I asking for in this case? I say, what is the probability someone's a beachgoer and they don't exercise?
B union A complement.
Okay. Now go backwards one. I want to state it differently. You're right. So what is that? That's called set subtraction. No, that won't help me in the calculation. But would that be this? I'm taking the beachgoers and I'm eliminating the exercisers from the beachgoers. So now what am I looking at? I'm looking at that, aren't I? So Samuel is correct. If I do it using unions and intersections, it'd be the probability of a beachgoer intersect, not an exerciser. But now not an exerciser is everybody outside of this circle, isn't it? So that includes these people here, and it includes these people here, but I said you have to be a beachgoer. So it's just these people here. So in this case, thinking of it as a set subtraction might be easier because we set up our circle correctly. Everybody okay with that? So what is the answer either way? 0.1. I don't have to do anything. I can just read it. Only 10% of San Diegans go to the beach and don't exercise. And the key was and don't exercise, not or don't exercise. We said at the same time. Okay. Let's keep going. Question 6. What is the probability a slacker also goes to the beach? What do I mean by a slacker? You know.
Doesn't
Somebody who doesn't exercise, exactly. If you look up slacker in the dictionary, I think that's what it says. All right, that's my definition of slacker. What is the probability that a slacker also goes to the beach? Is this an intersection or a conditional? What's my sample space now? Slackers, non-exercisers. That's my sample space, period. You with me on that? My sample space is non-exercisers. So how do I write this one? The probability somebody's a beachgoer given they're not an exerciser. Because again, I made it clear that my sample space is the non-exercisers. And which of those go to the beach? Now, in my picture, the non-exercisers are all of these guys. What percentage of San Diegans are non-exercisers based on my given information?
40%.
40% of San Diegans are non-exercisers. That's what that says right there. So I'm only talking about those people. They are now my sample space. Do some of the non-exercisers go to the beach? Yeah, we just answered that in the previous question. These are the non-exercisers that go to the beach. So what is this? This would be the probability of B intersect E complement, which we just did there, over the probability of E complement. My numerator we just did. That was the previous question. One of the harder parts of this is not the mathematics. No. It's the interpretation, the translation. Do you agree with that? In other words, sometimes it's easy to see, oh, I'm only asking an intersection. Other times, oh, it's a conditional probability. So what's my denominator here? So this is 0.25 or 1/4. So knowing the condition changes the sample space most of the time. It's not always the case, okay? It's not always the case. So we're gonna, I'm gonna define something, okay? Give me a what if. Okay, just the general A and B. We know that the probability of A given B equals the probability of A intersect B over the probability of B. We know this. What if? What if the probability of A given B is the same as the probability of A? In simple English, what if knowing the condition doesn't have any effect at all?
Mutually exclusive.
No, because that would mean there's no intersection. There's another word. There's another word that people always confuse with mutually exclusive. Independent. This is the definition. We'd say then A and B are, and the key word independent. The vast majority of the time, events are dependent. These events are obviously dependent. How do I know? Because the probability of A given B, or excuse me, the probability of B given E, or the probability of E given B, we calculated, but it was not, neither one of those were equal to these probabilities, were they? Right? My conditional probabilities were not equal to the given individual probabilities. So we would say they are dependent, or not independent. The vast majority of time, things are going to be independent. Excuse me, the vast majority, they're going to be dependent. But every now and then, knowing something occurred may not have any effect. Interesting. Okay? Let's go back to the dice roll for a moment. You guys still have your dice roll chart memorized in your head? If I said, what's the probability that my sum is even? Isn't that exactly half of them?
Yeah.
Everybody agree with that? Exactly half. If you go through your dice roll chart, 1, 1, 1, 2, 1, 3, 1, 4. Every other one would be even. All right? I want to know what's the probability that my sum is even. Okay, you just told me 18 out of 36. Oh, one of the dice squirted out and it landed, a 4. It landed a 3. You saw what the other die was. Well, it turns out, knowing that information, I just reduced my sample space. But still, exactly half of those outcomes are still going to be even. If one of my dice is a 4, then the other one's going to be even if it's a 2, 4, or 6. It's going to be odd if it's a 1, 3, or 5. Do you agree with that? If you saw one of my dice squirted out, it was a 1. Now it's going to be an even sum if it's a 1, 3, or 5 on the other die, odd if it's 2, 4, or 6. Does that make sense? If I'm asking the probability of an even sum, and now you know what one of the dice is, you've just changed the sample space, but it's still going to be exactly half. So knowing that information, changing my sample space did not affect the overall probability. Isn't that interesting? So that would be a situation where the events, an even sum, and the event, knowing one of my dice is a certain number, they would be independent because one did not affect the other's probability. The probability remained the same. So that's what we call independent. Now, here's another formula that's always true. The probability of A intersect B is always equal to the probability of A given B times the probability of B. I just multiplied out. This is always true because we're just working backwards. So let me throw a what if at you. What if A and B are independent? This, by the way, this is a formula that is always true. If A and B are independent, then tell me about the probability of A intersect B now. It would be the probability of A times the probability of B. Ooh. Now, the universal error I've seen made by a bazillion students is somehow or another, in every class I've ever taught probability, and all students automatically tell me, oh, the intersection is always the product of the probabilities. And that's true 1 out of infinity times. Yeah, it is actually true on occasion. Look at this example here. Is the probability of the intersection equal to the product of these probabilities? No, that is an extremely rare thing to occur. To assume it's true means you're going to get the wrong answer pretty much always. No, you cannot calculate an intersection. I said that on the first day. It's not mathematically possible to calculate an intersection. You can only count an intersection. So, could you have told me whether these events were independent without doing any work whatsoever in this problem? Yeah. 0.4 times 0.6 is not equal to 0.3. Therefore, this is not a true statement. Therefore, they are not independent. That's the simplest check there is. If I wanted to test whether my events were independent or not, if the product of the probabilities of the events equals the probability of the intersection, they're independent. That's very rare, but it can happen. In my dice roll example that I just gave you, that would have happened in that situation. Or you can just straight up definition. I'm given this, I calculated this. In our example that we did, the probability of being a beachgoer knowing you exercised was not equal to the probability of being a beachgoer. The probability that you exercised knowing you were a beachgoer was not equal to the probability you exercised. Okay? And the probability of the intersection was not equal to the product of the probabilities. So there's really 3 different ways I could have come to the same conclusion. Okay? Everybody cool with that? So it's actually a fairly simple process.
So for number 5, how come we don't divide the answer?
Oh, because I'm saying I want these 2 events at the same time. I'm saying, what's the probability someone goes to the beach and they don't exercise? Neither one of them's, my sample space isn't the beachgoers, my sample space isn't the exercisers. My sample space is everybody, and I'm only interested in the people They go to the beach and at the same time don't exercise. So I'm interested in that group right there.
Okay.
This is why it's tricky. The next question I said was, I have somebody who's a slacker. I'm only looking at the group of slackers. Which ones of those go to the beach? Oh, so I'm looking at all of these people, and then that was my numerator. That's why those were different questions. Did you see that?
Yeah.
This is why I said before, the language is hugely important. There's nothing about the calculations that is troubling in any way. You gotta admit, this is as simple as it gets from a calculation standpoint. It's all about interpreting it correctly because the language sounds similar. But if I said, what's the probability of this thing and this thing both happening? You know that's an intersection. What's the probability of this thing or this thing? You know that's a union. What's the probability of this thing knowing that thing happened? That's a conditional. Everybody cool with that? So this example here, right? This is a little bit tricky. Now, I'm going to give you one that's maybe a little closer to home because I've seen these numbers now. I don't know how accurate they are because the numbers change every year. But at Mesa College, think about it logically. If you're in a physics class, are you probably in a math class? If you're in a math class, are you probably in a physics class? Yeah. If you're not in a math class, are you probably in a physics class? If you're not taking math, are you probably in physics or probably not in physics? Probably not. If you're not taking physics, might you still be taking math? Yeah, but I'm going to use those as an example. So let's say at Mesa College, let's say 60% of the students are enrolled in a math course. I don't know if that's the exact number, but I know it's probably pretty darn close. Okay? What percent of the students do you think are enrolled, let's say, lab science? We'll broaden it. Do you think it's going to be the same number of people or a lot less? Probably a lot less. Let's say 20% are enrolled in a lab science. That could be physics, that could be chemistry, and technically biology because there's a lab. And let's say that 15% are enrolled in both. There's a lot of questions, and it's the same type of problem. I'm going to ask you slightly different questions. Find the probability a math student is enrolled in a lab science. How about a lab student is enrolled in math? And the third question, are the events enrolled in math and enrolled in lab science independent? Okay? Let's answer the first two questions before we answer the third question, because we're going to see there's actually multiple ways I can correctly answer the third question. So I need to define the events. Don't just start by writing probabilities all over the place and calculations, because I actually need to define things so that I can have numbers. So what do you want to call your events? How about M is enrolled in math? Keep it simple. And S enrolled in lab science. science. Then M intersect S is enrolled in both. What am I given? I'm given these. You say, wait a minute, you're talking about percentages of students enrolled in a class. Where's the probability come from? What's the probability a Mesa College student is enrolled in math? It's 0.6, because 60% of them are enrolled in math. That's simple translation. You never, ever use percentages in a calculation. Never. In any context, use percentages. I can say in all the years I've been teaching, I've never seen a student get an answer correct when they use percentages because they don't realize a percentage, 60% is not 60. So when people use percentages, I get probabilities that are really large sometimes. What's the probability that Jordan's going to get an A in the course? 4,000%. Yo. Kind of silly math, but all right. So what's probability of math? 0.6. Science, 0.2. Both, 0.15. All right, now let's answer the questions one at a time because we have to translate the language into the question. The first question is what? Using these symbols, what am I asking in the first question?
P of M given S.
It's the second question.
Yeah, let's get it.
What's my sample space in the first question?
The math students.
Math students. I'm looking at the group of math students and then asking what's the probability they're in science. Does that make sense, Art?
Yeah.
So that's the translation. That's where we get in trouble. I'm reading that and I'm reading things in the order they're stated and automatically putting my variables. No, I'm telling you I'm drawing from a math student. That's what I know. What's the probability they're in a science class? So it's the probability of lab science given math. What's the second question?
What I said the first time.
That's the reverse, exactly. But I'll get them both right in the wrong place. Well, no, I'll get them both wrong. I don't want to do that. So this is the probability of the intersection over the probability of math. And again, the simple explanation is I just reduced my sample space only to the math students. I don't need to draw a Venn diagram. I could, right? It's not entirely necessary. So this would be what? 0.15 over 0.6, and that's 0.25. What's this one? This would be the probability of the intersection. And again, it doesn't matter what order I write the intersection. Over the probability being in science, and that's 0.15 over 0.2. Question 3, are they independent? First of all, is it a yes or a no? It's not a maybe at this point, okay? What is the probability of, hold on. The first one, what's the probability of S given M? Somebody doing before class is swapping out all the caps. I'm trying to do this in blue. The probability of S given M equals 0.25, which is not the probability of S. The conditional probability is not equal to the original probability. The probability of M given S, where's that one? That's right here, is 0.75, and that's not the probability of M. Both of these are valid reasons. And what's the third? The probability of the essence. Do you agree that's it? That is an absolutely valid reason. That's a valid reason. That's a valid reason. All three of those give me the same conclusion. I don't need to do all three. I need to do one of those three. So if you had calculated this and you got 0.25 and go, wait a minute, the probability of being in science is 0.2. The conditional probability is 0.25. They're not independent. I didn't get 0.2 back again. Right now, I know they're not independent. Right now, I know they're not independent. I could have answered that at the very beginning of the problem. That product is not equal to that. They're not independent. But understand, all three ways are valid. Okay? Comparing the conditional probability to the regular probability, or doing the product of the probabilities and seeing if it equals the product of the intersection. I had to tell you the probability of the intersection. You couldn't calculate the probability of the intersection. Okay? Everybody understand? I have to tell you that in this situation. Any questions? Okay, we're going to move on to something a little more complicated, but very, very cool. I'm going to introduce something called Bayes' formula, Bayes theorem, but I'm going to make this minor because it's an application of this. It's one of the most important applications of this. If you had statistics, you maybe talked about it. You probably didn't, because it's kind of complicated for a lot of folks. It would have been sort of in the middle of the class, not at the end of the class. Okay. We're going to do the math, basically the mathematics of drug testing. Blood samples. Okay, so let's say, I'm going to give you numbers to make it easier. In a population of 1 million people, there's exactly 1 million people, just because we want to keep it really simple, okay? A rare disorder occurs 0.1% of the time. We always start with rare disorders. Something that's a common disorder is hardly even a disorder if everybody has it. So we have some rare blood disease. And let's say it occurs in 0.1%. That's 1 out of 1,000 people. Okay, this is a reasonable thing. I always say blood disorders. Now, most people realize later we're talking about a failed drug test. It's exactly the same thing. the failed drug test, in other words, if you're on drugs, that's going to be the disorder. But this is the mathematics of drug testing, but it's also the mathematics of, any type of disorder. Now, we have a test for the disorder. Now, here's the tricky thing. You have to understand this. A number of years ago, I had a young lady in a class. She was probably 19, 20 years old. And they suspected there was something wrong. They suspected she might have breast cancer or something. There was some irregularities in her blood test. And so they call her and they said, we need you to come in and bring a loved one, bring somebody close to you. Now, how would you interpret that? They just did a test for cancer, and they said, bring someone in. And they brought their parent in to tell them, oh, you're good, you're clear. I don't know, a phone call just saying you're good would have been, this poor girl, and she actually dropped out of school. She was so upset because she knew what the diagnosis was going to be, and it turned out it wasn't. Here's the thing, there's a test, it's usually a blood test, to determine if there's something wrong. If you had cancer, wouldn't you want to know as soon as possible? The worst thing you could have happen is that you didn't know. I have a very close friend. He was having all sorts of difficulty. This is a long time ago. All sorts of difficulty. He was an athlete and he couldn't move his arm very well. So he went in and they said, oh, it's probably a pulled muscle. This went on for weeks and weeks and weeks. He goes back in, they decide to do a blood test. He had a tumor that was the size of a softball in his chest. He had lymphoma. It had spread to every inch of his body and was going to his brain. They said, basically, good prognosis, you have 6 weeks. They misdiagnosed him multiple times over several months. He immediately started chemo and radiation, and him and his wife had a baby about 3 years later, by the way. He's still around. He completely beat it, which is, they gave him 6 weeks. Lymphoma is one of those you don't come back from typically. And the fingers of the tumor literally was head to toe. He was aggressive in the chemo and radiation, he was strong, and that's amazing. The point being, any type of test to find like a cancer, you want that test so strong that there's no way they could miss it. You want that test to be 100%, and for the most part, tests like that really are 100%. So if that test is so strong to catch any form of cancer, what is it also going to catch? False positives. By the way, it's an absolute, it is impossible to have a test that is so good that it catches everything and not catch false positives. A simple example, this has happened on multiple occasions. You're an Olympic athlete. They get drug tested constantly, especially if you get the gold medal. And today, before your event, you had a really good breakfast and you had a poppy seed muffin. And then later when you got your drug test, your blood test later, what did you test positive for? Opioids. By the way, that's an absolute. It would be impossible not to test positive for opioids. Why? Where does opium come from? Poppy seeds. You had a poppy seed muffin, you didn't take any drugs. You had cold, so you took some Sudafed before you competed today. You tested positive for ephedrine, which is an illegal answer. What is Sudafed short for? Do you know? Pseudoephedrine. That's what the acronym, that's what Sudafed is. Ephedrine is the strongest decongestant there is. It's also an illegal drug. You're going to test positive because there are similar effects in your body. So we have to understand that any form of test that we want, and think of it in a positive way. If you have a disorder, you want to find out so you can deal with it. Most tests aren't 100%, but most are so close. We'll just say the test is going to catch 100% of the time. Okay? The test, let's say, catches 100% of the disorders. If you have the disorder, you're going to catch it. If I said 99%, it wouldn't really affect the numbers. But there are, let's say, 5% false positives. That's actually quite realistic. Okay? We want that test to be so good that if there's even a chance you have it. See, what happens if you tested positive? They're going to test you again. And then they're going to say, oh, that was a false positive, because now we're going to do another test and you don't have it. But if you have it and we miss it, then we're not going to be able to cure you. So you have to understand that's why this is so important that we understand this. Now, you live in this place, and the way most testing, or if it's drug testing, they do what they call double blind. In other words, everything's coded so we can find out who it was, but you submitted it, I don't know it was you, and there's no way I can know who it came from. It can be found eventually, but I don't know, you don't know, and I run a test on it, and let's say a test comes back positive. Okay, find the probability the person actually has the disorder. Okay, everybody understand my question? So there's 1 million people in this city. I'm using 1 million so we can actually see physical numbers. It makes it a little easier sometimes. And 1/10% of the people in this city have a disorder. We know that because let's just say that's the general population. All right, so you did a blood test. You can translate that as drug test, but you did a blood test. The test comes back positive. Does that mean you have the disorder? You might be one of those 5%ers, right? So what's the probability you actually have the disorder? So this is a conditional probability. Now, in a stats class, we'll often use a bar for the complement. I'd say let's just keep using complement for the complement. So let's say that D is you have the disorder. D complement is you don't. Okay? There's only 2 people in this town. You have the disorder, you don't. What is the probability you have the disorder?
0.1%.
So 0, 0, 1. The probability you don't would be, okay? Let's say P is the probability of a positive test. Okay? So P is positive test. What is the probability of a positive test given you have the disorder? What is the probability of a positive test given you don't have a positive? That's also given. Just to make it easy, what's the probability you test positive given you have the disorder? 100%, so 1. We like that. And in real life, that number is always going to be close to 1. No one's ever going to say it's perfect, but they're going to 0.999. But what's the probability of a positive test given you don't have the disorder?
0.05.
That's what's called a false positive, by the way. Okay. All of these numbers are given. All right. What's my question? What's the probability of the disorder given you tested positive? It's not the same as this, is it? Because this is, you have the disorder. We're going to catch it 100% of the time. This is, you don't have the disorder, you're going to test positive 5% of the time. By the way, it would be nice in reality if we could lower that number, and in some cases it is. But the closer this is to 1, the bigger this has to be, because you got to catch the fringe. People who are in the early stages, okay? None of you would know this, but pregnancy tests. Are pregnancy tests 100% accurate? No, they're pretty darn accurate. If you're pregnant, I've never heard of somebody being pregnant and it coming out not pregnant. I have heard of somebody not being pregnant and it came out pregnant and they tested again and it was fine. That'd be false positive. Because you want that test to be so subtle. COVID tests. Did anybody here take a COVID test at home? I can't count how many. Right? I can't count. I did the testing every 2 weeks during the first year of COVID. I would go to the places just to make sure. And I did the home test. I can't count the number of times. But that test is really, really accurate. But is it possible that you have COVID and it missed it? They're saying actually that wasn't possible. But it was possible that you didn't have COVID and it came back positive. Now, sometimes you tested too soon. Sometimes you but no test was perfect. But we tended to trust it because it was very accurate. Now let me draw a picture, all right? I have 1 million people in my town. How many have the disorder in my town of 1 million people? 1,000 people have the disorder, agreed? And how many don't have the disorder? Okay, now, positive, negative. Of these 1,000 people, how many are going to test positive? All 1,000. How many are going to test negative? 0. Of these people, positive, not positive. Well, get out your calculator. What's 5% of 999,000? That'd be 49,950 positive tests. How many are going to test negative? Everybody else. So what's that? 940,050. Does that sound about right? I'm in the lab. The test came back positive. What is my sample space?
49,950.
Yeah, my sample space are the positive tests only. The question is, what's the probability you have the disorder? Well, what's my numerator? 1,000. Let's do this calculation. About what? About 0.02. You all agree? It's about 0.02. Okay, that number is great, right? So I have a positive test in my hand. What's the probability that person actually has the disease or the disorder? About 2%. That means that of all the positive tests I have, 98% of them are incorrect. Is there something wrong with this mathematics? No. It's absolutely perfect. This happens all the time. Here's the problem. I have a positive test. It's 98% likely to come from a person without the disorder. Why? because so few people have the disorder that the vast number of positive tests are gonna come from the false positives. Even if I reduce this number down to 1%, that number wouldn't make a big difference.
as much as the.
So does everybody understand this is the problem? Now, how many in your lifetime have ever heard an athlete just got busted for doping, and of course, in their press conference, what do they always say? I didn't do anything, I'm innocent. Have you ever heard, kind of like every athlete, you know, whether they did or not? My favorite though, I'm drawing a blank, it was probably close to 20 years ago. It wasn't Lance Armstrong, it was one of his peers. He was an Olympic cyclist, he won a gold, and tested positive, and they said his level of testosterone, I don't remember the exact numbers, but it was absurd, like 50 to 100 times what a normal. And in his press conference, he said, no, I wasn't doping, I'm just that much more of a man than everyone else. It was something to that effect, which I thought was the greatest line ever. He was stripped of the gold and banned for life, by the way. You know, that's funny, of all the sports that exist, the highest percentage of doping is cycling. And you look at those guys, those are the skinniest dudes, but it's for the endurance and the leg strength. I mean, we all know, you know, the Lance Armstrong story. Years and years and years he denied it, and finally came out and said, yeah, I was always doping. In fact, never was he not doping at any point, even before his cancer. So the thing is, we never believe the athletes when they say they're clean. But if only a small percentage of athletes, were doping, then that would mean that the vast majority of the positive tests came from people who were actually clean. So that's why whenever they do this, they always take 2 samples. If the probability of a false positive is 5% and we do 2 samples, you actually would multiply those probabilities. The probability of you testing positive twice in a row would be 0.5 times 0.5. Now that probability is very small, isn't it? So if we've done a second test and you test positive again, it's highly likely, yeah, you actually have the disorder. We'll call it the disorder again, okay? Because you tested positive twice in a row, it's far less likely that it's a false positive. But what often happens is you tested positive, ooh, let's go test it again, okay, you're negative. Because we do have false positives. If you have a false positive, it doesn't mean you're gonna test positive every time. No, you tested positive on that one test. Understand, right? It doesn't mean forevermore you are doomed to test positive, okay? This is crazy. Now, I wanna work backwards and say, what did we actually do to get this answer, okay? Because I drew a picture and I gave you the numbers of the population. I'm asking you exactly the same question, and I wanna take that out. Because shouldn't the answer be the same regardless of the size of the population? I used 1 million people for one simple reason. Then we have nice, big, happy, round numbers. And it's really easy to see everything that went on. You with me on that? So how can I do this using conditional probability? Well, let me erase this a little bit. What was my numerator? Technically, what was my numerator?
Probability of D and P.
It was the probability, sorry, off to the side. How about over here, if I said, what is the probability of P given D? We know that's the probability of the intersection times the probability of D. Agreed? Let's leave that right there. We know that. And then the probability of, let's see if we got the rhyme. And then the probability of P given D complement was the probability of P intersect D complement. Now, this is hard to read after a while. Times the probability of D complement, okay? So in my picture, what did I actually use? Which parts did I actually use? I actually used, make sure I got the right things here, the probability of P given D and I multiplied that by, make sure I got the right thing, probability of D. There we go. Yep, okay. Because I had an intersection. Now, what's in my denominator? What is my numerator? These are all of the people, basically, that have the disorder. Or people have the disorder, and what do I want in my denominator? All the positive tests. So in my denominator was going to be the probability of a positive D times D. Sorry, I'm going to have to erase this right now. Plus the probability of a positive given D complement times probability of D complement. This was my denominator. So my numerator were the my numerator were the folks with the disorder, my denominator were the positive tests. Okay? This is called Bayes' formula, or Bayes' theorem. I don't need you to know the formula. It actually can get very complicated. But the way we did it by drawing a tree, I think makes it really, really simple in general. Saying, okay, here's another one I like to do. I do this in stats class. We actually spend time. All right? In a particular election, let's keep it really simple. You have Republican, Democrat, and let's just say other. Other would be, every other. So let's say in a particular election, you have 55% Democrat, and you have 40% Republican, and you have 5% others. In this particular election, voting. Not who's winning, but who's voting. Now, let's say that among the Democrats, we know what percentage actually vote for the candidate and what percentage vote for somebody else. In the Republicans, and I'm talking about the candidate who is whoever won. In the Republicans, we have the percentage who voted for the candidate and the percentage who voted for someone else, and then we have the others. Okay? So if the probability that you voted for the candidate given you're Republican would be a certain number, the probability you voted for the candidate given you're Democrat, and so on. Does everybody understand? We know this from things like exit polls. You're leaving the site, and if you've ever been asked, it's real simple. They'll say, do you mind, who did you vote for, and what are you registered as? That's it. They're not going to ask you any other questions because they're trying to tally numbers. The reason they do this is so they can report partial results during the physical election. So you've all seen this. So you're watching the news, and they'll say, this state, some state on the East Coast, we're giving to this candidate, like say for president. But our polls haven't closed yet. How could they do that? Well, because in the exit polls, they asked so many people, and it was overwhelming from the people they asked. In other words, it's usually correct. But they're doing this to just it'd make more sense for just wait for the election to be over, I think, personally, to give results. It's sort of like, I'm grading the exams, and Jordan wants to give me updates. So every 15 minutes, okay, problem 3 is looking pretty good, Jordan. I'm almost ready for 4. Took a break on 5 for a moment. I'm getting back to it, so I'm giving you updates. Now, you'd rather just wait for me to be done. Agreed? I mean, we laugh, but that's kind of what we're doing during elections. So I've got all of this information, right? Here's the percentage in each party. Within each party, here's the percentage that voted for the candidate. Great. Now, I'm actually looking at a ballot, and this ballot voted for the candidate. What's the probability that person was a Republican, or the probability that person was a Democrat, or the probability that person was another? It's this problem. We know this probability, but I reversed it to ask the question. We don't know this probability. It's a complicated calculation. Okay, so let's keep it real simple. Zachary and Mandy, they're shooting free throws, and they're just having fun. They're just taking turns shooting free throws, and they're going in all the time. And let's say you make a certain percentage, and you make a certain percentage. Let's say you took a certain number of shots, you took a certain number of shots. Keep it simple. Maybe you took 100 shots, you took 80 shots. You made 75%, you made 80%. Just pick numbers. So I turn around and I see the ball go in, but I didn't see who took the shot. What's the probability it was you? What's the probability it was you? Does everyone understand that's this problem? What's the probability that you make a shot? What's the probability the shot went in given you took it? I know that number. What's the probability, given that the shot went in, what's the probability that you took it versus you took it? Ooh, That's a completely different problem. It's exactly what this is. This is kind of the reverse. And it's the one that kind of defies common sense at first. This is why I'd rather draw a picture when you're doing this problem. So when I ask this question in a class, I usually limit it to two choices. Although one of my favorite questions I'll ask in a stats exam, it'll be the basketball question. It'll be, Mo, Larry, and Curly are shooting shots, and of course Mo takes 60% of the shots, Larry takes 30, and Curly only takes 10, and Mo makes 75% of shots, and Larry makes 80% of shots, and Curly makes 90% of the shots. A basket was made, what's the probability with Mo? Same problem. What's the difference? You now have 3 things on the denominator that you're adding, but it's the same question. That's what Bayes' theorem is. It's the probability in reverse. But I like introducing it because it is the mathematics of blood disorders and, or if you want to call it, drug testing. Why? Because of the existence of false positives. We don't care about false negatives. False negatives are so rare and so small. A false negative would be, of my 1,000 people in this population that have the disorder, and everybody got tested, one of them didn't test positive. Oh shoot, that's terrible. That means we can't help that person. But the false negative is extremely rare. We're trying to eliminate a false negative by making the test so strong that it catches everybody, thereby introducing false positives. Does that make sense? Why you can't have a 0 false positive if the test is going to catch everything? Because if it's going to catch everything, particularly in the early stages, are there biological changes that can be happening in your body? Maybe you have a funky reaction. You're taking some form of medication and you had a strange reaction to it. And at the same time, we're testing you for cancer or something. But your strange reaction, right, might set off the cancer test as being something that could potentially be cancer, but it wasn't. It was a reaction to something else. The poppy seed muffin, right? Showing up as opioids in your bloodstream. Because the blood test doesn't distinguish where it came from or what, it's just there's some form of opioid. Does that make sense? So that's why this is really cool math in general. I'm only scratching the surface. I'm only introducing it. Okay? Any question on this? This is the primary application of conditional probability is this. This is special. I wanted to show you that just because it's cool, it's interesting. But how many have had stats and you did Bayes' theorem? Did anybody? Did you spend any time on it?
Sometimes, yeah.
So you remember doing stuff of this nature?
Yes.
And by the way, would you all agree that nobody saw this result coming? That kind of blows you away? It's like, oh my gosh. Because we usually talk about rare disorders. Now, what's the only way, this is terrible by the way, what's the only way that I can improve upon this? We had 98% of our positive tests came from healthy people. What's the only way we can change that and make it, that all the positive tests are coming from the people with the disorder?
Make the test less effective.
Or have a much higher percentage of our population have the disorder. See, the only way the drug testing can be more accurate is if a higher percentage of people are actually using performance-enhancing drugs. Then the positive tests are actually coming from the people who are using it. That, by the way, that's not a good solution. Would you agree? Those have more people with the disease, then all the positive tests will be coming from them. No. So it's having a test being less sensitive, but then we run the risk on the other side, right, of not catching it. And I don't know that that's a good trade. All right, pop that. We are now finished.